Chapter 7, Project Design, Layout, and Implementation. When we save a river, we save a major part of an ecosystem, and we save ourselves as well. Tim Palmer. Introduction. Since induced meandering is a method for restoring dynamic stability to incised stream channels, it is necessary to determine whether or not the channel is indeed incised, and, therefore, a suitable candidate for restoration using this method. Deeply incised channels that are relatively straight provide good induced meandering opportunities. Gullies that have some bends may suggest where to start the meander layout. This may help, but the existing pattern can also complicate matters. Gullies formed within the confines of old roads or irrigation ditches make good candidates. Streams which have been deliberately channelized, deepened and straightened to enhance drainage efficiency, such as old flood control projects, are also appropriate. Streams with floodplains bounded by highways, railroads, and urban development may also be deeply incised, but not advisable for treatment because of possible risks to infrastructure. If causing a stream to meander would put valuable infrastructure at risk, it would not be a good candidate site for induced meandering. When considering the implementation of any induced meandering project, the first question to consider is, what will be achieved, short-term and long-term? What are the overall goals for the creek and the land? Induced meandering involves time, money, and labor. Is there enough of all three to complete the project successfully? Will the restoration project increase the productivity of an agricultural operation, benefit wildlife, or improve water quality and flow modulation downstream to meet regulatory requirements? Is the restoration in response to an altruistic impulse to heal the earth? The goal will influence how the induced meandering project is approached. Having a holistic, well-considered goal for healing the land will improve the chances for successfully restoring the creek. The first step in the planning and design of a project is the careful assessment of opportunities, as well as a realistic evaluation of potential limitations to project implementation. Photo 7-1. Planning must take into account the geomorphology of the selected area in comparison with a suitable reference reach, and weigh possible treatment options against the difficulty of applying them. Implementation must be feasible in terms of accessibility, materials needed, social, economic, and political constraints, the wishes of the landowner, and, of course, fundraising realities. Planning the implementation must conform to various federal, state, local, and tribal laws, regulations, and ordinances, which may vary in substance or application from place to place and time to time. Project continuity. The project leader must follow through with the entire process of assessment, survey, planning, design, construction, monitoring, and maintenance, and must be present on the ground to direct every facet of the project in order to ensure fidelity to the design. More than once, the authors have left instructions for the subcontractor, landowner, or volunteers to complete relatively straightforward on-the-ground work, only to return to find serious errors in implementation. 7-3. The fault must be borne by the project designer for breaking with project continuity. The devil is in the details. Do not leave the details to others. A project planning and implementation checklist appears in Appendix H, page 209. Preliminary assessment. A preliminary assessment begins by studying a map of the watershed or by looking at the area by using Google Earth, or similar programs. The next step is to walk the stream, conducting a visual assessment of the impaired wetland riparian system, including the areas upstream and downstream of the project area. Follow through by conducting a detailed reconnaissance of the stream reach of concern. What are the physical constraints, characteristics of the reach? Are there fences, property boundaries, rock outcrops, or perhaps irrigation ditches that have to be accommodated? What is the hydraulic regimen of the channel? Perennial, intermittent, or ephemeral? What is its ecological condition? What is the primary water source? Snowmelt, summer precipitation, or groundwater from springs? What are the political, economic, and social realities regarding possible treatment? What are the prevailing land use issues, and how will they affect planning and the likely outcome of treatments? Note that if livestock are present, grazing management objectives and operations should be coordinated with stream restoration goals for best results. Poor cattle management can delay or set back the riparian response of an induced meandering project. Uncontrolled herbivore grazing can destroy newly established riparian vegetation, thus affecting long-term success. Potential grazing impacts should be taken into consideration before implementing a restoration effort and management adjusted accordingly. The same can be said of roads. Successful restoration must take into account three things: the creek, the client, and the client's relationship to the creek. This book is about creeks, not psychology. Sometimes it may be necessary to walk away from a project if the landowner's objectives or practices are not compatible with realistic treatment options. The next step is to conduct a Rosgen Level 1 geomorphologic survey of the project reach and determine the Rosgen stream channel type. What is the slope of the channel versus its valley? What is the channel pattern? What is the nature of bed and bank materials? How cohesive are the banks? What are the sources of sediment? Is there too little or too much sediment? What is the bank erosion hazard? Are the banks well vegetated or only sparsely so? Is the vegetation aquatic, upland, or riparian in nature? What is the apparent trend in channel evolution at this time, and how advanced is the process toward reaching dynamic stability? An optional step is to conduct a proper functioning condition survey. This is a qualitative method for assessing the condition of riparian and wetland areas in reference to how well the natural physical processes are functioning. Lotic environments, running water habitats, are considered to be in proper functioning condition when the appropriate hydrology, vegetation, and sediment regime are present to 1. Dissipate stream energy associated with high water flow, 2. Filter sediment, capture bedload, and aid in floodplain development, 3. Improve floodwater retention and groundwater recharge, 4. Develop root masses to stabilize stream banks, 5. Develop diverse channel characteristics that provide the habitat and water depth, duration, and temperature necessary to support greater biodiversity such as fish production, waterfowl breeding, etc. When reading the landscape and identifying impacts, there are endless landform combinations to discern and consider. Chapter 6. Are there clear signs or incision such as abandoned channels on the terrace, headcuts, or lack of a floodplain? Are there recently exposed roots? What is the stated problem here? What natural stream channel evolutionary sequence is occurring? What is the likely next step in channel evolution? Could intervention be used to reverse or speed up the evolutionary process? What is the goal of the project? The preliminary assessment should lead to one decision: to treat or not to treat. If it's not broke, don't fix it. Be cautious and consider the upstream and downstream effects of stream treatment. What collateral damage to resources might occur to offset gains made by timely intervention? What could be the worst outcome if treatment failed? Might a flood wash away a railroad trestle or $1 million home? The boundaries of the project reach should not only take into consideration the wishes of the landowner or land management agency, but also the goals of the funding agency and potential liabilities for planners and builders. Often, an area selected for induced meandering will contain incised reaches that are intermingled with stable reaches in properly functioning condition. The properly functioning reaches of a stream may be the ideal reference condition for comparing with the rest. In many cases, the overall project design may involve the use of induced meandering treatments intermingled with natural channel design, simple revegetation, and no treatment at all. Selecting the project reach requires conducting a reconnaissance level survey on foot to identify opportunities and potential constraints that might preclude meander development. The ultimate product resulting from this survey is a determination of the feasibility of implementing an induced meandering project or projects and the length of reach or reaches to be treated. Ideally, the initial survey will be supported by available topographic maps, property plats, GIS images such as Google Earth or other visual aids. Figure 7-1, page 143. During the survey, it is important to note the Rosgen channel type of any reaches or subreaches that vary in character from the rest of the channel. Where necessary, separate the project reach into bioreaches. The central characteristic of a bioreach is that its geomorphology and plant community are relatively constant throughout and contrast with the geomorphology and ecology of adjacent reaches. If the project area contains segments that differ significantly from each other, it will be necessary to divide the area into distinct reaches with separate restoration goals, objectives, and treatment plans. For example, a bioreach with perennial flow will require a different treatment plan from an adjacent ephemeral reach because different plant and animal adaptations will produce different responses between the reaches. Select a reference reach. Success will depend upon selecting a stable stream reach or reference to use as a template for the restoration design. Reference reaches must be dynamically stable channels in the same valley type as the project reach. As discussed in Chapter 4, the reference reach for an induced meandering project will be a Rosgen B or C stream type, depending on the evolutionary sequence the project stream is following. Figure 4-2, page 73. Reference reach scenarios, in order of preference, are a stream segment within the project reach, a segment upstream or downstream of the project reach, a segment from a nearby stream, a distant stream. If no reference reach can be found, mathematically determine stream channel dimensions from appropriate tables and formulae. This is an acceptable last option for determining stream channel dimensions for projects in remote, small watersheds. Conduct appropriate surveys. At this point, it is necessary to conduct a Rosgen Level 2 survey of both the project reach and a stable reference reach, if available, to determine reference parameters, departure from the reference, and dimensionless ratios. This step includes a plan view survey, longitudinal profile, typical cross-sections, and pebble counts. Use the Channel Morphology Field Sheet, Appendix G, page 204, to record these data. While doing the longitudinal profile of the project reach, it is helpful to pound stakes on the right bank of the creek every 200 feet and clearly mark the stations on the stakes. This will save time when laying out the design, especially if the locations of the stakes are plotted using a sub-meter GPS unit. All elevational benchmarks and cross-sections should be monumented to facilitate future monitoring as well as project layout. This is also a good time to complete a sketch map of the reach, do baseline vegetation surveys, and establish permanent photo monitoring points for baseline photos. Chapter 8. Establish geomorphic goals. Establish realistic geometric goals for the project reach and compare these with current parameters. Use the Channel Morphology Field Sheet, Appendix G, to record project goals during this process. Certain parameters may not apply to all projects, but these data are necessary to determine the current channel type and its potential. Meander length, L, maximum depth, D, max, and bankful width, W, BKF, are the three major points used to design an induced meandering project. Meander length, sometimes referred to as meander wavelength, is the main variable used for designing an induced meandering project. The valley length of the project reach is divided by the meander length to calculate the number of meanders needed for the reach and to select the locations of deflectors needed to indicate meander formation. Below are recommended methods for obtaining the three main channel measurements in descending order of accuracy. Roman numeral 1. Use the project stream reach as its own reference reach. A reference reach template can be assembled from the stable segments of the project area or reach. Using the stable features of the project reach as a guide for treating the unstable segments makes practical sense because the geomorphology of the banks is sculpted by the same set of flows. This is the most accurate and direct method of obtaining these important variables. The minimum data for a reference reach are the bankful width, bankful depth, and the meander length. For future reference and monitoring, additional data such as the species and vigor of the vegetation, the radius of curvature of stable bends, and the width to depth ratio of stable riffle sections can often be gleaned from stable parts of an impaired stream. Roman numeral 2. Look upstream or downstream from the project reach. If there is no useful information within the project reach, search both upstream and downstream in an effort to find suitable reference sites. Pay close attention to tributaries entering between the project reach and the reference reach. These will change the watershed area, requiring the use of scaling factors for the stream channel dimensions. This is described in Method B. A recently, or not so recently, abandoned channel on the terrace can serve as a reference reach if it is still intact, and bankful width, bankful depth, and meander length can be distinctly identified. Roman numeral 3. Use another stream as a reference reach. A reference reach must be a Rosgen B or C stream type, depending on the evolutionary scenario for the project stream. It must be in the same valley type and have similar channel bed materials. A tributary may serve the purpose. Since the reference reach is unlikely to have the same watershed area as the project reach, the meander length, bankful width, and bankful depth will have to be scaled to match the watershed area of the project reach. This is described in Method B. Roman numeral 4. Mathematically determine stream channel dimensions. Reference reach. What reference reach? It is all too common in the desert Southwest to find that all the streams in the region are in disequilibrium. In this case, there will be no reference reach to model for the stable form, and the designer must use mathematical relationships instead. Stream channel dimensions can be mathematically modeled and results checked against any stable features in the project reach. These mathematical methods in descending order of accuracy are discussed below. Method A. Scaling meander length from reference reach data. If a stable subreach within the project reach has developed a floodplain and a defined bankful channel but does not have discernible meanders, this is the most accurate proxy method for obtaining meander length. Note that the bankful width needed is the width that a stable C or B channel type would have in that stream reach. The dimensionless meander length, Lm, is first calculated from the reference reach as follows. Lm equals L over W BKF, where L equals reference reach meander length, W BKF equals reference reach bankful width. Then the dimensionless meander length is used to scale the meander length for the project reach. Example, Lm equals 14.2. Reference reach dimensionless meander length. W BKF equals 15 feet. Desired bankful width of the project reach. Lm times W BKF equals L to 14.2 times 15 feet equals 213 feet. This is the meander length for the project. Method B. Scaling meander length using watershed areas of reference and project reaches. If there are no bankful indicators in the project reach or vicinity, then use the following formula to estimate what the bankful width should be based on the relative sizes of the watersheds of the reference and project reaches. The bankful width is proportional to the square root of the watershed area. W1 over square root A1 equals W2 over square root A2. 2. W2 equals W1 times square root A2 over square root A1, where W1 equals bankful width of reference reach. W2 equals bankful width of project reach. A1 equals watershed area of reference reach. A2 equals watershed area of project reach. Watershed area of the reference reach, A1, is 7 square miles. Bankful width of the reference reach, W1, is 13 feet. W2 equals 13 feet times square root 10 over square root 7 equals 15.5 feet. The desired bankful width for the project reach. Meander length from the reference reach can now be scaled by the ratio of bankful widths, as in method A. When there are no reference reach data of any sort available, meander length is determined from regional curve data and the width to depth ratio for the C stream channel type. Step 1. Consult the regional curves to determine the bankful cross-sectional area, A, BKF. That would be expected for the watershed area of the creek. Example: watershed area is 4 square miles for an ephemeral stream channel in New Mexico. The regional curve predicts a bankful cross-sectional area, ABKF, of 10 square feet, figure 7-2. Bear in mind that, due to natural variability, actual cross-sectional area could vary by 50%. Using a curve that has individual data points instead of an averaged curve helps remind us of the range of variability. Step 2. Using the desired stream type from the geomorphic goals, determine the W/D ratio for the bankful C or F channel. Example: W/D equals 30. Step 3. Determine the appropriate bankful width for the desired stream type using the following formula. WBKF equals square root of A BKF times W/D, where A BKF equals bankful cross-sectional area derived from the regional curve. W/D equals the width to depth ratio for the desired channel. Example: square root 10 feet to the second times 30 equals 17.3 feet bankful width. Step 4. Determine dimensionless meander length, LM, figure 7-3. Example: LM equals 16. This is an appropriate dimensionless meander wavelength for a high sediment supply ephemeral dryland stream with moderate vegetation cover. Step 5. Compute the meander length L from the formula below. LM times WBKF equals L. 16 times 17.3 equals 277 feet, the meander length for the project. LM times WBKF equals L. 16 times 17.3 feet equals 277 feet, the meander length for the project reach. Alternate method C. This method applies if regional curves are stratified by stream type. At the time of printing, these data are not available in Arizona or New Mexico. Determine WBKF for a C channel from the regional curve for the watershed area. Example 1.
Suppose that, according to regional curves, the bankful width for a C channel in a 4 square mile watershed should be 20 feet. Further suppose that the bank consists of materials that are moderately cohesive and resistant to erosion, and a dimensionless meander length of 14 seems appropriate. LM times WBKF equals L to 14 times 20 feet equals 280 feet, the meander length for the project reach. The distance between meander apices, or half a meander length, is 140 feet. The distance between the meander apex and the crossover, or 1/4 of a meander length, is 70 feet. Dimensionless meander length, LM. LM decreases with increasing. Vegetation cover, base flow duration, bank cohesiveness. LM increases with increasing. Sediment supply, flow variability, slope, bank erodibility. Figure 7-3. The more cohesive the stream bank, because of the bank material itself or the density of vegetation, the lower the ratio of meander length to bankful width. The lower the number, the more stable the banks. In the southwest, perennial streams range from 10 to 14 and ephemeral from 14 to 18. Meander schematic, project dimensions. Total valley length equals 400 feet. Meander length equals 200 feet. 0 feet, 100 feet, 200 feet, 300 feet, 400 feet. Elevation, 5,125 feet, 220 feet. Bankful width equals 20 feet. Elevation, 5,120 feet. Quarter meander length equals 50 feet. Half meander length equals 100 feet. Meander length. Bankful width times dimensionless meander length. 20 feet times 10 equals 200 feet. Number of meanders in valley length. Valley length divided by meander length. 400 feet over 200 feet equals 2. Half meander length. Distance between apices, 200 over 2 equals 100 feet. 1/4 meander length. Distance between apex and riffle, 100 over 2 equals 50 feet. Channel length. Meander length times sinuosity. 200 feet times 1.1 equals 220. Percentage slope. Differences in elevation between first and last riffle divided by channel length between first and last riffles. 5 feet over 330 feet equals 1.51%. Figure 7-4. Meander schematic. Example 2. If the bankful channel width should be 20 feet according to reference reach or regional curves, and banks consist of clay materials that are cohesive and resistant to erosion, use the multiplier of 10, figure 7-4. 20 feet times 10 equals 200 feet equals meander length. Half a meander length is 100 feet, the distance between meander apices. Quarter of a meander length is 50 feet, the distance between apex and crossover, or riffle. If meander length is known from a reference reach, for example, but the multiplier is not, divide the meander length by the bankful channel width to get the multiplier. Example, 200 feet over 20 feet equals 10. Develop a vision for the restored reach. Rise up, O dusty river, rise up, flow free once more, cast shining rays and dewdrops upon a greening shore. Bill Zeedyke. Having conducted a Rosgen Level 2 survey, try to visualize the stream in its restored condition. What would be its highest potential state of recovery? It is not enough to visualize stable, well-vegetated stream banks. The vision of the restored reach should include such geomorphic factors such as depth, bank height, entrenchment ratio, width sinuosity, width to depth ratio, as well as ecological factors such as type and condition of riparian vegetation. Describe how the restored reach will look 5 and 10 years after project completion. Base the vision on a realistic interpretation of both the Rosgen Level 2 survey and the Proper Functioning Condition survey, as tempered by the political, social, economic, and physical setting and the wishes and desires of the landowner. In other words, what is the best that one could hope for, all things considered? For example, a perennial stream having a sinuosity of 1.2, width-depth ratio of 18, a dimensionless meander length of 11, a dimensionless belt width of 3, and bounded by a riparian forest dominated by Gooding willows. The accuracy of the visualization will depend on experience, knowledge of reference conditions, and the physical realities of the site. Consider additional treatment options and site requirements. As previously stated, induced meandering is but one method for restoring damaged streams and applies only to incised channels. For damaged Rosgen type B, C, E, or D channels, other methods, such as natural channel design, are more appropriate, especially when high-value property is at stake. If city or county codes require hard engineering, it may not be legal to use either induced meandering or natural channel design. For example, in developing plans for the restoration of the Santa Fe River within the city limits of Santa Fe, the authors were obliged to consider both approaches, depending on the characteristics of a particular reach, ownership constraints, and economic values at stake. Where city or country ownership provided sufficient space and site conditions allowed, induced meandering was recommended to reinstate a meandering channel with an accessible flood plain. But where infrastructure or ownership rights interfered, planning restored to engineered treatments, such as revetments, groins, and rock mattresses in compliance with sound engineering practices and local ordinances. From another standpoint, when attempting to establish appropriate bed control, channel dimensions, and bank stability, many other treatments and practices are available from the literature and other practitioners. One should not feel obligated to use only treatments prescribed within these pages. The authors strongly urge the use of natural channel design principles wherever an alternative to an induced meandering practice is needed, based on geomorphic, ecologic, legal, or economic conditions at the site. Project design. Select starting and ending points. Deliberate care should go into the selection of the upstream and downstream boundaries of the project reach, because the choice will have a direct bearing on long-term channel stability and how well the calculated meander pattern fits within the physical constraints of the valley setting and the potential for recreating an active floodplain. It is critical in any stream restoration project that involves grade control to be sure that the downstream end of the treatment reach is well protected from down cutting. An ideal downstream boundary is composed of a stable reach, exposed bedrock, a boulder waterfall, a well-designed road crossing,
or other stable bed features.
Select a starting point for the first or most upstream meander apex or meander crossover. Some options might include an existing meander apex, a stable bed control feature, a stable bank feature such as a large boulder, or a culvert or road crossing. An ideal upstream starting point may be a stable horizontal control feature such as large streamside boulder or rock outcrop, a dense willow patch, a downstream edge of an armored road bank, or a bridge abutment. Pay close attention to tributaries entering the treatment reach. The confluence with a significant tributary will define a reach boundary. There will be a significant change in channel morphology due to the increase in watershed area, which must be accommodated by the design. The confluence may be represented by a transition zone extending over a considerable length as the flows merge, or identifiable as a narrowly defined point along the channel profile. Tributaries can also supply a different size, type, or annual load of sediment and can sometimes provide extra moisture for plant growth. Alternative downstream boundaries of a project reach might include ending the project at the point where the incised reach merges with a non-incised stream segment, at a point where the meander pattern generated within the project reach would carry forward naturally to effect a smooth merger with the untreated reach, or at some naturally or artificially hardened control point or segment not readily altered by induced meandering treatments. A property boundary is not a good choice for arbitrarily ending a project reach unless the boundary happens to coincide with a natural grade control or a suitable location to build a very good artificial grade control structure.
Meander layout. If no accurate satellite image, aerial photo, or GIS map is available, start with a sketch map of the creek, or create a meander schematic, figure 7-5. Establish half meander length locations, proceeding downstream from the first meander apex. These will become approximate locations of new meander apices and the sites of installed baffles or veins. Place a mark midway between meander apices. This will become the approximate location of a weir, riffle, or bed control feature. Lay out the meanders on the plan, taking into consideration all natural features on the map. Often existing infrastructure at streamside or perched on a nearby terrace will suggest options for meander layout. It is sometimes easier to work with an artificially created, perfectly straight channel with no constraints than with a channel exhibiting some sinuosity. What can be done to increase sinuosity where some already exists? Sometimes constraints simplify the solution of a problem. Sometimes constraints simplify the solution of a problem. Whatever meander layout is proposed for the creek, it should fit all significant existing meanders. Is there a beautiful tree or a large boulder in the way? Adjustments of up to 20% of the meander length can be done to accommodate vegetation, existing meanders, or other site-specific details. Accommodating natural features of the site in the design is a vast improvement over imposing a purely mathematical layout on the landscape. This is where the designer may face difficult challenges. If there is a severe layout problem, skip a section and then pick up the meander layout at a logical point downstream. It is not necessary to create a series of relatively uniform curves in the design. Look at a natural stable watercourse to confirm this. Sometimes there are two right bends in a row. Return to the project reach and transfer the trial design onto the creek with pin flags. Measure structure locations from the station stakes that were placed during the longitudinal profile survey. During this process, make adjustments to further accommodate natural features and the microtopography of the site in the design. Halfway between two consecutive deflectors, there will be a grade control structure. Sometimes there is a re-entry point from an overflow channel near a site for a grade control structure. Proceed carefully. Critique the design and make any desired changes to the locations of the pin flags until the plan flows like a river. Go home and sleep on it. Come back in the morning. If necessary, remove the pin flags and start all over again until the design feels right. Determine appropriate materials and sizes for structures. Make a decision about what material to use for the deflectors and weirs based on the channel substrate as well as what materials are locally available, preferably on site. Consider the size of the watershed and anticipated flood forces that the structures will have to withstand in order to be effective. If the bed and banks are sand, silt, or clay with few stones, wicker weirs and post vanes or baffles are the ideal structures to use. Their installation is relatively easy for small creeks in these bed substrates, and the structures will stay put like a stick in the mud, which is what they are. Importing cobbles or boulders for use in the stream may prove inappropriate, as they will tend to dig themselves into the highly erodible bed and disappear unless the footers are very deep. If working by hand, post structures become increasingly difficult to install as the bed aggregate gets more gravelly and cobbly. Under these conditions, stone structures become more appropriate. If working with a backhoe, post structures can still be easily constructed in a gravelly, cobbly bed. Digging a deep trench for the posts and backfilling with dead men and stones will ensure that the posts do not get ripped out in a flood. See photo 7-9, page 160. Where the bed and banks are armored with embedded cobbles and boulders, induced meandering may not be effective because the banks will resist erosion and increased shear stress will be transferred to the structure, causing it to fail. Structure size is based on the bankful width and the bankful depth of the stream. It is critical that structures be properly sized. Chapter 5. Complete treatment inventory, permits, and clearances. Inventory structures and treatments. Once a meander schematic has been created, prepare a thorough inventory of all structures, planting, and earth-moving activities specified in the design. This formation is essential for creating a project budget and applying for any required permits. Using the worksheets from Appendix G, make a list of structures, compute quantities of required materials, and calculate volumes of dredge and fill to be moved. Figure 7-6, page 152. Determine if suitable construction materials are available on site and what will have to be imported from elsewhere. Determine equipment needs and any limitations to its use, and identify access routes and specific erosion control needs. Prepare and apply for permits, clearances, and permissions. The following is adapted from an article in Quivira Coalition's July 2008 bulletin with text and information provided by Neil Schaefer from New Mexico Environment Department Surface Water Quality Bureau and Jim Wood from the U.S. Army Corps of Engineers, retired.
Depending on factors such as land status, jurisdiction, environmental requirements, state and/or tribal and/or funding sources, implementation of a stream restoration project may require some form of federal, state, tribal, or local permitting. The Federal Clean Water Act, CWA, passed in 1972, recognizes public environmental values and protests the chemical, physical, and biological integrity of waters of the United States, while segregating point source and non-point source pollution, i.e. pollution which cannot be traced back to a single origin or source, such as stormwater runoff, water runoff from urban areas, and failed septic systems. One of the innovations of the CWA was Section 404 permitting, which ensures that our nation's waters are protected from irresponsible and unregulated discharges of dredged or fill material that could alter or destroy these valuable systems. One way the federal government regulates non-point source pollution is through Section 404 permits and Section 319, which includes a popular funding source from the Environmental Protection Agency EPA, 319H water quality grants for the voluntary implementation of best management practices, BMPs. 404 permitting. Section 404 of the CWA requires approval prior to discharging dredged or fill material into waters of the United States. Unlike most other provisions of the CWA, which are administered by the EPA, Section 404 is administered by the U.S. Army Corps of Engineers, USACE. So, before starting work in a stream, lake, or wetland, landowners are encouraged to consult with the USACE, who will issue written verification that the proposed work falls within permit coverage. Typical activities requiring Section 404 permits include depositing of fill or dredged material in waters of the U.S. or adjacent wetlands, site development fill for residential, commercial, or recreational developments, construction of revetments, groins, breakwaters, levees, dams, dikes, and weirs, placement of riprap, road fills, stream crossings, culverts, fords, and bridges. Do you need a Section 404 permit for your project? In general, Section 404 permitting would be required for projects that involve placing fill within an active stream channel or adjacent wetlands within the protected waters of the United States. Before proceeding with a project, you should ask yourself, is the project located within a water of the United States? Due in part to recent U.S. Supreme Court decisions, this jurisdictional determination has become complex, essentially requiring consultation with the USACE. Is the proposed activity regulated under Section 404? Section 404 regulates certain activities associated with placing fill within waters of the United States. It generally does not regulate other activities such as trash dumping or driving equipment through a stream. It also does not specifically regulate excavation. However, this is getting into a gray area that essentially requires consultation with the USACE to avoid possible violations of federal law. What type of Section 404 permit will I need? The USACE has created general permits to cover similar kinds of work that commonly do not result in significant impacts. The most common of these are the nationwide permits. For example, Nationwide Permit Number 27 covers aquatic habitat restoration, establishment, and enhancement activities. The Quivira Coalition's Riparian Restoration Project on the Dry Cimarron, Union County, New Mexico, required federal 404 nationwide permit number 27 and state 401 permits for both hand-built and machine-built structures. Photos 7-5, 7-6. These permits may include conditions such as, in some cases, a pre-construction notification to the USACE. The authors encourage applicants to consult with USACE. Section 401, State Certification. The federal CWA has several sections that address the obligations of the states to maintain water quality. Title III of the CWA describes state programs, including state water quality standards. Title IV of the Act begins with Section 401 certification, which provides states and tribes the privilege to certify federal permits that may affect water quality. Thus, all Section 404 permits require state certification, and the certification effectively becomes part of the permit. These conditions may be waived, granted, conditionally granted, or denied. Under federal law, this certification is to ensure compliance with state water quality statutes and regulations. Information for New Mexico residents. Section 404 permitting and 401 certification serve several purposes in New Mexico. First, they provide a means for the New Mexico Environment Department, NMED staff, to simply become aware of projects that might affect water quality, thus allowing them the opportunity to monitor for water quality standards exceedances. This permitting system is also an excellent outreach opportunity, allowing NMED staff to interact with applicants regarding design, construction methods, and ways to prevent or mitigate impacts to the state's waters. Finally, Section 404 permits and 401 certification allow NMED to mandate conditions for the project, thus creating a legal framework to enforce protection of federal, state, and tribal waters. On tribal lands, the tribes or EPA issue the 401 certification. NMED only issues certifications for waters of the state. Other states have similar offices and authorities. Depending on land ownership and project funding sources, some projects may also require cultural and/or threatened and endangered species clearances. Implementation. For project implementation to proceed smoothly, it helps to be very organized and well prepared. Create a to-do list. Pre-implementation tasks should include staking the project reach, creating a timeline for on-the-ground work, coordinating calendars with contractors, organizations, or volunteers, arranging equipment rentals, and making sure all needed tools and supplies are available. Based on meander length calculations and the project layout map, mark or stake meander lengths on a trial fit basis. Photo 7-7. Mark the location for each meander apex. The location of apices can be adjusted to match bed and bank features up to plus or minus 20% of the meander length. Proceeding downstream from the first meander apex, establish half meander length locations. These will be approximate locations of new meander apices and the sites of installed baffles or veins. If a natural apex is encountered, adjust the locations of the structures to accommodate it. Place a marker midway between meander apices to approximate the location of a weir, riffle, or grade control feature. Determine the average difference in elevation per meander and half meander, change in elevation from top of riffle to top of next riffle, to calculate slope, Chapter 3. This is used to construct the weir to the proper height to match the planning slope. Once the project has been staked, create an implementation timeline and choreograph the order of entry for the work to be done. For example, if equipment will approach from a specific access point, plan to work upstream from that point so that the equipment can be easily removed from the site once work is completed without disturbing completed structures. If using heavy equipment, this is also a good time to review the condition and location of access routes. Organize labor, supplies, materials, equipment, and hazardous spill abatement kits, and coordinate calendars with equipment rental companies, landowners, subcontractors, and material delivery. Also, arrange for proper safety and fire gear and make sure that all laborers and volunteers are aware of on-site hazards and safety protocols and procedures. Once all permits have been obtained, on-site implementation can begin. It is best to plan ahead for materials preparation, trimming pickets, and stockpiling of materials on site.
Bank shaping. It is often desirable to start a curve and widen the channel opposite a baffle by excavating material and placing this on the inside of the baffle near the bank. A starter pool can be dug with a pick and shovel opposite the apex of the baffle. This will help saturate and soften the soil on the opposite bank, accelerating lateral erosion. If incorporating bank shaping into the design, mark these places with pin flags or marking paint. Marking paint does not stick to the water surface very well, so it is best used only in dry arroyos. Plant material. If there is a high enough water table or available irrigation to ensure survival, deflector structures should be planted with appropriate riparian vegetation. Planting of baccharis or true willows should be done for one structure length upstream and downstream of the apex of the vein or baffle. Conversely, plants should be removed from the opposite bank if they will inhibit meander development and planted at a suitable nearby location. Post-implementation mapping. Once all structures have been constructed, GIS mapping of their locations will assist in evaluating the ecological and hydrological success of the treatment. Figure 7-7, page 156. Project demobilization. The goal is to leave the area neat, tidy, and in stable condition. Once work is complete, clean the work site of all trash, extra materials, supplies, tools, and equipment. Reseed and mulch the area if needed, and close tracks and roads made specifically for the project. This is also a good time to make repairs and do routine maintenance on tools and equipment in preparation for the next project. Return rental tools and equipment. With the landowner or land manager, do an on-the-ground site visit of the project to review completed treatments. Submit a notification of completion to agencies and other parties if required. Minimalist induced meandering applied to a New Mexico drylands stream. The goal of induced meandering is to establish a stable meander pattern. This is accomplished by building deflectors in the stream channel at the proper spacing to initiate a series of alternate bends. The side-to-side motion of the water moving through these bends as the stream flows down the valley might be thought of as an harmonic oscillator. In other harmonic oscillators, such as a swinging pendulum or a weight on a spring, the oscillation is started by disturbing the weight from its equilibrium and activating the restoring force. The restoring force accelerates the weight back towards the center, and the resulting momentum carries the weight past the point of equilibrium, thus starting the oscillation. It is not necessary to push the weight back and forth in order to start or increase the amplitude of a harmonic oscillation. When starting a child on a swing, only one push forward is needed, and once she is swinging high enough, only a push every once in a while is required to continue the motion. The same principle can be applied to the design of an induced meandering project having the minimum amount of deflectors necessary to establish the desired pattern. This approach has advantages. Having fewer structures in the channel saves time, money, and material. It is lower risk and has a higher aesthetic value. Having a deflector for every desired bend can create problems. Deflectors have the effect of narrowing the channel for a short length. Deflectors on both sides of an already narrow gully require grade control structures to prevent bed degradation. Using a vein to deflect flow to the opposite side of a channel may change the angle of attack at the next downstream vein, creating an unpredictable outcome. Baffles and veins have been alternated. Baffles and veins have been alternated on several projects to avoid this phenomenon, baffles requiring more posts than veins. Perhaps the simplest induced meandering design might consist of only one vein for every 2 bends, without the use of grade control structures unless there is a specific problem in the project reach, such as a head cut or the risk of continued down cutting. Comanche Creek, Comanche Point Gully, One Rock Dam, Rock Baffle, Zuni Bowl, Cobble Rundown. Figure 7-7. Comanche Point Gully was created by livestock trailing in a 54-acre watershed at 9,000 feet elevation. After treatment, this steep gully evolved from a Rosgan A to a Rosgan B channel type for most of its length. Maps of structures locations created by Michael Bain using Google Earth for Quivira Coalition. A restoration project in southwest New Mexico was designed by Van Clothier with this type of layout, and so far the results have been promising. The creek drains a sandy 45 square mile watershed that is dominated by summer monsoonal thundershowers. Within the client's property, a head cut progressed upstream during the February 2005 flood of record. The flood lowered the channel bed by 2 to 3 feet for well over 1,000 feet of channel length. The erosion occurred because historic overgrazing had replaced the native riparian vegetation with shallow-rooted, non-native Bermuda grass. An old road went up the floodplain, crossing the creek diagonally in several places. It is likely that these crossings contributed to the instability and resulting incision. One part of the restoration effort relocated the road to a suitable upland site and addressed the head cut, and another part, described below, attempted the minimalist approach to induced meandering. The stream reach affected by the head cut had evolved into a long, straight channel that ran down the base of the right terrace cut bank for approximately 1,000 feet, as that cut bank gradually dropped in height from 10 feet to 3 feet. After the 2005 flood, no riparian vegetation remained within the flood-prone area of the ephemeral stream reach, and the channel bed material consisted of sand and small gravel. The recent erosion destroyed whatever bankful features might have been present in this reach, so a reference reach was sought to provide the missing information. A carefully selected riffle cross-section was obtained in a stable, well-vegetated reach 500 feet upstream from the top of the head cut at station 4318.5. This was used as the reference reach. Note the factor of 8 vertical exaggeration in the graph, figure 7-8. Reference reach statistics. Entrenchment ratio, 3.2. Bankful width, 28.3 feet. Bankful mean depth, 1.4 feet. Bankful maximum depth, 2.1 feet. W/D ratio, 20.2. Bankful cross-sectional area, 38.4 feet squared. Riffle to riffle slope, 1.3%. Channel bed material, sand and fine gravel. This reach classifies as a Rosgan C4 channel type. Consulting Moody's Regional Curve for New Mexico, a 45 square mile watershed would have a bankful cross-sectional area of approximately 33 square feet. Moody, 2003. Considering the natural variability of stream channels, this is very close to the 38.4 square feet obtained from the reference reach. From the cross-section graph, the only other candidate for bankfull was the top of the terrace at 105.3 square feet for bankfull cross-sectional area, which is too far off the average to be considered. A cross-section in the impaired reach was conducted at station 5710.5. Since there were no reliable bankfull features in this eroded and unstable channel, the bankfull line was set at the known bankfull cross-sectional area of 38.4 feet squared from the reference reach to allow Rivermorph software to compute the floodplain access ratio for classification purposes. Figure 7-9. Note that the break in the side slope below the bankfull line, which represents 26.3 square feet of cross-sectional area, is not a candidate for bankfull, even though the area is within the natural variability, because this break in slope represents not a depositional feature, but an erosional one. It is an incision in the historic stream channel, and only marks the current progress of the gully's widening since the headcut's recent upstream passage. Cross-section 5710.5 statistics. Entrenchment ratio 1.7. Bankfull width 35.6 feet. Bankfull mean depth 1.1 feet. W/D ratio 32.4. Bankfull cross-sectional area 38.4 feet squared. Riffle to riffle slope 0.7%. Channel bed material sand and fine gravel. This classifies the impaired reach as a Rosgen B4C channel type at the beginning and transitions to a C channel 1,000 feet downstream, but through both channel types it is wholly without meanders. Accommodating natural constraints. There are two bedrock outcrops within this degraded reach. The first is on river left at station 5,300 feet, and the second is on river right at station 6,700 feet. This gives a channel length of 1,400 feet in between and a constraint requiring any channel pattern to meander around the bedrock outcrops. Since these outcrops are on opposite sides of the channel, the solution will have odd number of half meanders, figure 7-10. In using 5 half meanders as a trial solution, a half meander length would be 280 feet, 1,400 feet over 5. A full meander length would be twice as long, or 560 feet. The meander length ratio is the meander length divided by bankfull width. Using 28.3 feet for design bankfull width from the reference reach cross-section, the meander length ratio would be 19.8 feet, 560 feet over 28.3 feet. In ephemeral sand bed streams with sparse vegetation, the range of the meander length ratio is typically 13 to 18. Figure 7-10 presents an array of possible solutions to the bedrock constraint. There is only one solution within the normal range, the one with 7 bends corresponding to a meander length ratio of 14.1 and a meander length of 400 feet. Constraints can be helpful because they reduce the number of possible solutions. In this case, they forced a unique solution for the meander length ratio. If there are any additional constraints, such as a group of trees, individual meander lengths can be adjusted up or down approximately 20% to go around them. Induced meandering layout. Since the impaired reach ran along the base of the right terrace cut bank, the plan called for installing one vane per meander on that side to kick the thalweg away from the cut bank. This design allowed the stream the freedom to turn back towards the base of the cut bank wherever it would, thus creating 2 bends per structure. Figure 7-11, page 160.
The location for the first vein was marked on the ground at station 5500. This was a half meander, or 200 feet, downstream from the upper bedrock outcrop. 2 more veins were marked on the right bank at a spacing of 400 feet at stations 5900 and 6300. The station of a post vein is defined here as the point where it departs from the bank because this is where the point bar will eventually form. Using layout string, stakes, and a tape measure, the angle of departure from the bank for each vein was set at 20 degrees. The veins were designed like barbs pointing upstream and were marked to protrude across 60% of the bankful channel width. See Chapter 5 for a more detailed explanation of post-vein design. The layout line was traced on the ground with spray paint, and the stakes and layout string were removed to use at the next site. Photo 7-8. Construction. Operating a backhoe in the dry channel bottom, a trench 4.5 to 6 feet deep was dug along the marked line, and the dirt was placed on the channel side of the trench. Juniper posts, 8 feet long and 6 to 12 inches in diameter at the base, were placed upright along the shoreward side of the trench with the butt ends down and spaced to allow a 6-inch gap between posts at the ground level. The trench was carefully backfilled with the loader bucket, with a spotter holding the posts to keep the proper spacing. Photo 7-9. Once the trench was filled and tamped down by the backhoe, the row of posts was marked for trimming at the correct angle of descent. String was tied to the bank end post at a height of 2.1 feet above the thawweg, which corresponds to the bankful maximum depth from the reference reach cross-section. The string was stretched tight along the row of posts and tied to the channel end post 4 inches above ground level. This line was marked on all posts with spray paint. The posts were then cut with a chainsaw, producing a row of posts that descended from a height of 2.1 feet at the bank to 4 inches at the other end. Flood testing. During the summer monsoon season of 2006, there were 3 moderate floods and 1 over-bankful event. In 2007, there were 2 moderate floods and 1 bankful event. The vein structures held up well despite several posts shifting in the trenches. Vein 2 started to sculpt the channel by collecting flood debris, causing deposition of sediment near the bank in the vicinity of the posts and forcing the thawweg away from the bank. Photo 7-10, 7-11. Willow saplings and forbs have started to colonize the sediment deposits. A base flow channel initially went through vein 3, photo 7-12. Perhaps the vein was too aggressive, sticking too far into the channel, or a post moved. The base flow channel is being colonized with vegetation and therefore should fill in over time. Many posts shifted slightly in their trenches during the first flood because the loose backfill material was on the downstream side. The meandering process has begun. In retrospect, it would have been better to place the posts on the stream side of the ditch and use deadmen, horizontal posts, and any available small boulders in the bottom of the trenches to keep the posts secure. This modified construction technique is now standard practice. Induced meandering condensed. Choose a small stream reach or gully to be treated. Walk the watercourse and select that portion which seems to be the most stable and the most representative of the desired future condition for the project reach, your vision. It seems to be healing, has vegetated banks, a developing floodplain, and looks healthy. This is the quick and dirty reference reach. At the reference reach, measure the bankful width of the channel. Measure the bankful depth of the channel at the riffle or crossover area of one or more typical meanders. Measure the length of the typical meander in half meanders, the distance between meander bends. Record these measurements in feet yards, steps, whatever. Depending on the nature of the bed and bank materials, available workforce, landowners' wishes, etc., decide on the material type to be used for structures. Example, rocks, boulders, posts, pickets, wicker, or plant materials. Select the upstream end of the project reach and begin laying out and then building structures of the appropriate size and at the right spacing intervals to imitate the dimensions noted for the reference reach. How many meanders will be needed to treat the reach? How far apart? Watch for indications of an evolving meander bend. Build a baffle at the inside of the bend that will deflect stream flow and cause increased erosion of the outside bank of the bend. This treatment will exaggerate the meander radius, forcing the channel to lengthen and the grade to flatten slightly. Proceed to the next bend and repeat. Look carefully for indicators of an evolving meander bend. If the reach is straight and there is no bend at the appropriate distance, as determined from the reference reach, build a baffle to create a meander at that point. Remember, the channel should bend rhythmically, left and right in repeating pattern. Try to stay with the pattern, making allowances for well-established vegetation and other important features when necessary by varying the meander length plus or minus 20%. Continue installing baffles or vanes to create alternating left and right bends at the appropriate spacing intervals. Ask family and friends to help cut pickets and roll rocks so they can share in your accomplishment. You have now created a condition which will cause lateral erosion of the stream bank and promote point bar formation on the inside of the meanders. The new meander pattern will exaggerate any bends in the pre-treatment channel. Go back to the beginning and build a low weir, one rock dam or wicker weir, at the first meander crossover, i.e. approximately midway between the first and second planned meander bends. The weir should never exceed 6 inches in height and should have adequately deep footer stones or deep set posts to prevent removal by scour. The weir should be at least as long as it is wide. Continue downstream and build a weir at every crossover or intended crossover midway between adjacent meander bends. At some places, a grade control structure such as a Zuni bowl or rock arc dam or cobble rundown may be needed to control channel slope or to stop an existing head cut from eroding the channel bed. Build it. Complete the reach. Measure the overall length of the channel and valley length to determine sinuosity. Measure some representative cross-sections and take photographs that will document channel features such as width of channel, width of floodplain, and density and vigor of stream bank vegetation. Go away and wait for a rainfall event large enough to cause a bankful event. During the rainstorm, return to the project and wait for a flood. If the flood comes, run up and down the stream, taking photos of your structures with water flowing over them. After the flood subsides, observe, measure, and rephotograph the channel, noting obvious results or lack thereof. This step is called monitoring. Did vanes or baffles create lateral bank erosion where you wanted it? Have the pools deepened? Is the floodplain wider? Maintain, repair, modify, remove, or relocate structures not performing as expected. This step is called adaptive management. Plant willows, cottonwoods, sedges, wild roses, and currant bushes on the new floodplain. If the channel has changed or evolved in the direction that more closely resembles the reference reach, you have successfully implemented induced meandering. Congratulations! Celebrate with your remaining friends, if any. Reflect on your accomplishment. What's changed? What more could you do? Was it legal, moral, and ethical? Did the requirements of the Clean Water Act, the Endangered Species Act, and other pertinent federal, state, or county? What's changed? What more could you do? Was it legal, moral, and ethical? Did the requirements of the Clean Water Act, the Endangered Species Act, and other pertinent federal, state, or county regulations and ordinances apply? Better to check first. Summary. The design, layout, and implementation of an induced meandering project can be done by using bankful channel dimensions from a reference reach or calculating these dimensions from the regional curve if no reference reach is available. Regardless, when working with water, the devil is in the details. A thoughtful assessment of the project area, rigorous measurement of channel attributes in the reference and project reaches, careful selection of structure locations, disciplined implementation of planned structures as designed, and always mindful of site characteristics, full documentation of as-built features, and thoughtful monitoring will go far toward assuring that the devilish details are satisfied.